So we talked on the last chapter about finding the derivative of the function and all the rules that come with, here's the different function, tell me what the derivative is. In this next chapter, actually in the next two chapters, we're going to be talking more about ideas of what does the derivative tell us about a function. So if I have a function and you tell me the derivative, great. What can we talk about now that we know that derivative? And so we've talked already about how derivatives should connect with slope and slope of the tangent line. And so based on that, you should be able to kind of piece together what things we're going to talk about. The first big thing we're going to talk about is when our derivative is 0 or does not exist. If the derivative is 0 or does not exist, then it is what is called a critical point. A critical point is a point where the derivative is 0 or does not exist. So that's going to be our first key term. And the first thing we're going to be finding on these problems is a critical point. Where does the derivative equal 0 and where does the derivative not exist? And then based on that, we'll be able to get some information from there. And so the biggest thing that we'll have some information about is minimum and maximum. And that's what we're going to be focusing on today, is minimum and maximum. So first, we're going to talk about our definitions and break down those definitions. Maximum value and minimum value. The definition says we have a maximum value if and only if f of x is less than or equal to f of c for all x on D. So what that means is that, remember, whenever you see f of x or f of c or f of something, you should be thinking about y values. We're talking about y values here. And for all x, we have the y value for any x value being less than or equal to this specific value. This is a specific value. I'm just breaking down these definitions because especially if you get to a college math class, a big chunk of a college math class is, can you read math? Can you read the notation? So we're making sure we can break down a definition that you already have a good idea of what a maximum is, but we're breaking it down so that you can see what it looks like. F of x less than or equal to f of c for all x in the interval in our domain. So what that means is that any value, if I pick any value, it's either going to be smaller than the specific value we're talking about or equal to the specific value we're talking about. So in other words, what this is saying is that every other point is below f of c. Every other y value is below this specific y value. That's what makes it a maximum. It's the largest point. That's all we're saying here, is that it's the largest point. And same thing for minimum. We're saying that f of x now is greater than or equal to f of c. In other words, every point is larger than this point, than this specific point. And that should make sense because the minimum should be the smallest value. It should be below everything else. The only difference between this definition and the definition below it, when we talk about local extreme values, a local max or a local min, means that it is the smallest value in some smaller interval. So let's say that we have, this lets me say, let's say that I have like a cubic function that looks like this. Then this lets me say that this point is a minimum. It's not the smallest point, but it is the smallest point if I look in a kind of window within my function. If I focus in on a window within my function, I still have this point being a low point on the graph, but it's not the smallest point. So this still lets me say that this is a local, or another way that you might see it written as a relative minimum, but it's not an absolute minimum or maximum. An absolute minimum or maximum means that we have the smallest point on the graph. There's nowhere smaller or bigger than it on the graph. So that means that this does not have an absolute min or an absolute max, because technically it goes into infinity or negative infinity. But we can still say that it has a relative min or max. So with those definitions out of the way, the main theorem that we're going to use here is what's called the extreme value theorem. This is what we're going to focus on today. The extreme value theorem says if f is continuous on a closed interval a to b, then f has both a maximum value and a minimum value. So what we're saying is that if we just zoom in, use a basic function here. If we just zoom in and focus on, let's say we don't have a function that goes on forever. And let's say that it's just goes on to here. As long as we have a closed interval, meaning we're counting the endpoints, then if we're looking at a closed continuous function, then all that means is that we're guaranteed to have a largest value and a smallest value. It could be one of the endpoints, it could be something in between the endpoints, but we're guaranteed to have a maximum and a minimum. In this case, the maximum will be here and the minimum will be here. So our goal today is that we're going to use calculus to find where those maxes and mins are. So let's look at some examples. We're going to look at a closed interval, and we're going to figure out where the max and min is going to be. So our steps to do that are going to be, where does f prime equal 0 or not exist? And then check those critical points and the endpoints. The critical points and the endpoints, so that we know the critical points are where f prime is 0 or does not exist. So these are our candidates for our absolute min or max. We either have, we could have a minimum or a maximum here. We could not. But the candidates that we're going to have are these points that we find in step 1 and our endpoints. One of those points is going to be my maximum. One of those points is going to be my minimum. Let's start, actually, this is a more complicated example. Let's start with the simpler one. Natural log of x plus 1. So let's find the derivative here. Well, the derivative of natural log of x plus 1 is going to be 1 over the function. So 1 over x plus 1. We need the chain rule, but our derivative of x plus 1 is just 1. And so we're going to find where does this derivative equal 0? Where does this derivative not exist? Those are the points that we're interested in. And so this one is actually pretty straightforward, because h prime equals 0 where the top equals 0. That's where the derivative is going to be 0. So that's not going to happen. And then h prime does not exist where the bottom equals 0. Well, that's not very interesting because that's going to be at x equals -1, and x equals -1 is not in our domain from 0 to 3. So that's not a candidate either. So we have no critical points. So now all we need to check is our endpoints. We need to check our endpoints to figure out where our absolute minimum, absolute maximum are. So we need f of 0, and we need f of 3. We want to know what the y coordinates are. So that's why we're checking the original function to figure out what the y coordinates are. F of 0 is going to be the natural log of 0 plus 1. So that's going to be the natural log of 1. And you should know that natural log of 1 is asking e to what power is 1? What exponent do I need to put to get the answer to be 1? And that is 0. And then f of 3 is the natural log of 3 plus 1, which is the natural log of 4. So those are my candidates for the minimum and maximum. And so then we need to just figure out which one is bigger. Well, obviously, which one's bigger between natural log of 4? Well, that's positive, and 0. So that means that our minimum is at 0, 0. X coordinate is 0, and the y coordinate is 0. And our maximum is at 3 natural log of 4 was the y coordinate. And so 3 natural log of 4 is our absolute maximum. So while you're finishing writing that down, I'm going to talk about why are we interested in f prime where f prime is 0 and does not exist. Because f prime of 0, let's think about what that means. F prime of x equals 0 means we have a slope of the tangent line being 0. So that means we have a horizontal tangent. Well, if we have a horizontal tangent, then that's going to give us maximum and minimum, because it's telling us that our slope of the tangent line is about to change directions. And if it's changing directions, that means that we might have hit a smaller point or a biggest point. If f prime does not exist, f prime does not exist can mean a couple different things. It could mean that we have a vertical tangent. It could mean that we have a corner or cusp, in which case that could mean that we're changing directions as well. So eventually we're going to look for not just where this 0 does not exist, but does it change directions? And that's what we'll talk about more on Wednesday. All right, questions on that? All right, let's do one more together here. Let's go back to part A. Because in part B, all we had to worry about was the endpoints. But now we're going to have more to worry about. F prime of x equals, derivative here is going to be, well, that's x to the negative first, so that's going to be negative x to the negative second. And then derivative of natural log of x is 1 over x. And so I'm actually going to simplify this because right now we know where f prime does not exist. F prime doesn't exist at x equals 0 because that's where the bottom doesn't exist. But we want to figure out where f prime is 0. So to figure out where f prime is 0, we actually need to rewrite this a little bit. I'm going to get a common denominator. Equals negative 1 over x squared plus x over x squared, which means that we can combine these and just add these together. Means we have x minus 1 over x squared. So this is another way to write this function. So now if we're figuring out where f prime of x equals 0, well, that's where x minus 1 equals 0. So that's at x equals 1. So 1 and 0 are our critical points. Remember, because this caught some people on last year's AP test, we're going to talk about maxes and mins and other things. But when I talk about critical points, that just means that it's an important point to talk about. It means our first derivative is 0 or does not exist. Now we can start to say and make some distinctions here. First off, we don't care about 0. Why don't we care about 0? Because we're looking between 0.5 and 4. So 0 is not in the running here. So our candidates are x equals 1. That was our critical point. And then we have our endpoints. If we're finding an absolute max or min in between these endpoints. So at x equals 1, and then we want our endpoints. X equals 0.5 and x equals 4. So now we want to take those candidates and plug them in to the original function, because we're looking at what is the maximum and minimum. That's a question about the original function. What's our highest y value and our lowest y value? Since we're asking about y values, we're going to plug into the original function. So we want f of 0.5, we want f of 1, and we want f of 4. And whichever of these is the biggest or the smallest is going to be our max and min. So 0.5, 1 over 0.5 plus the natural log of 0.5. Equals, well, 1 over 0.5 is going to be 1 over 1/2. That's going to be 2 plus the natural log of 1/2. So we'll come back to that one. F of 1. Well, f of 1 is going to be 1 over 1 plus the natural log of 1. And we've already said that natural log of 1 is 0, so this is just 1. f of 4 is going to be 1 over 4 plus the natural log of 4. Calculator time. It's calculator time. It's time to plug these into our calculator and see which one of these is the biggest or the smallest. So at this point, I would say that we should plug these into our calculator and see what we get. Yes, f of 4 should be your largest number. This should be about 1.6. This is my maximum. So this was about 1.6. This one is about 1.3. And so this one, f of 1 being 1, is going to be my minimum. So my absolute max, the largest value, was the 1.6. My absolute minimum, my smallest value, was 1. So my critical point that I found ended up being my absolute minimum. And then the absolute maximum ended up being one of the endpoints.